Good morning, good afternoon, or good evening, depending on your time zone. Welcome to our talk, May the Trust Be With You, empowering TrustZone-M with multiple trusted environments. Just to give you a bit of color of who we are and what we do, my name is Sandro Pinto. I'm a research scientist and assistant professor at the University of Minho, where I currently lead the Embedded System Research Group and a number of very talented PhDs and master students. I'm also actively involved with a security startup from the Bay Area that you may know, that is X5. My co-speaker, Daniel, is currently pursuing his PhD under my supervision, and over the last few years, Daniel have worked closely to the industry in several R&D projects. You can definitely find us on Twitter, but also on LinkedIn, GitHub, ResearchGate, and so on. So this is the agenda for today. I will focus on the first 3 points, and then Daniel will go through the design, implementation, and evaluation of our solution. Let's start the whole story with one of the most used buzzwords of the tech world, that is the Internet of Things, or simply the IoT. So the IoT aims at connecting every single device to the Internet with the intention of disrupting societies and creating several social and economic benefits. The numbers are impressive and the market opportunity is definitely huge. I do remember when I was in Santa Clara back in 2017 attending the ARM-TechCon, and when ARM disclosed their projections on the road to the trillion IoT device by 2035. Well, one of the biggest challenges in the IoT is security, because by connecting every single device to the Internet, we are massively enlarging the attack surface on those devices. And the biggest problem is that first, companies have a lack of security experience, and second, devices are built without any kind of security requirements. And that's why what we have seen so far is a cat and mouse game of increasing hacks and patches. So just to recap, IoT devices have specific requirements, and these requirements first enlarge significantly the attack surface, and second, creates an enormous attraction for actors. Then the great majority of IoT devices are still being built around the traditional computing model, and when all code blocks are combined in a single memory space, there is no isolation. And ARM knew since day one there is a problem out there and they need to do something, and basically they have decided to include ARM TrustZone in their full portfolio. So the $1 million question is TrustZone enough? So the 3 key motivation points for this work were: first of all, we had this strong background on TrustZone, so we want to explore this new variant specifically built for MCUs. Second, and in the context of a different work, which I will talk later in this presentation, we have observed that the TrustZone classic dual world model is falling short to address the increasing requirements of modern devices. And thirdly, we decided to understand how we could leverage the existing TrustZone-M hardware building blocks to implement a multi-world approach. So let's go now through a quick overview of ARM TrustZone technology. ARM TrustZone was introduced back in 2004, targeting ARM application processors, the Cortex-A line, and the technology has achieved mainstream adoption in the mobile industry. In 2018, and basically to address the problem we have discussed so far, ARM decided to start introducing TrustZone in the new generation of microcontrollers, the so-called TrustZone-M. From an high-level perspective, both technologies are similar. I mean, the processor can execute either in the secure or non-secure state, but from a low-level perspective, there are significant differences in the realization of both technologies, mainly because TrustZone-M is quietly optimized for deterministic execution, low overhead, and low power. Well, the first big difference is related to the execution state. While in the Cortex-A processors, the security state is dictated by the 33-bit, the non-secure bit, in TrustZone-M MCUs, the security state is dependent from the memory space. And the memory space can be partitioned not only in secure and unsecure, but also in non-secure callable. Well, for those who know the ARM v7-M architecture pretty well, they know existing processor modes are thread and handler mode, with thread mode capable of running privileged and unprivileged software. Well, in ARM v8-M architecture, the security states are completely orthogonal to the existing processor modes. This means there is a replica of the thread and the handler mode for the secure and unsecure states. And of course, there are different privileges in terms of transitions between the secure states. For example, the secure software can explicitly call a non-secure function, but the opposite is not possible. I mean, the non-secure software cannot directly call a secure function. If that happens, a secure fault exception will be triggered. Well, to mediate transitions between the non-secure state and the secure state, which per se are sensitive, ARM has introduced this concept of non-secure callable. The non-secure callable area is the most similar mechanism to the monitor component existing in Cortex-A processors and provides a security entry point for non-secure software. These entry points need to fulfill specific requirements, such as the first instruction in the API must be an SG or a secure gateway. The question now is how memory and device are partitioned, since there is no TrustZone address space controller, neither the TrustZone protection controller. Well, in TrustZone-M MCUs, there are attribution units. There is the implementation defined attribution unit, IDAU, and the secure attribution unit, SAU. And basically, the result security state is the logical OR operation between both attribution units. So the IDAU provides static partitioning, and it's non-programmable and is specified and customized by the silicon vendor. On the other hand, the SAU provides dynamic partitioning. It is totally programmable, obviously in the secure state, and is always available on the chip. The single parameter that is tied to the vendor is the number of available memory regions, which typically is 8. So just to highlight and to give an example how the synergy between both attribution units work, let's take as an example the address 1000 to 1000. So it is defined as non-secure in the IDAU and as secure in the SAU. So the final result is secure. So you can see here the full truth table for this resulting security configuration. So the SAU and the IDAU are specific controllers at the core level, but when there is SoCs with additional bus masters such as DMAs, there is the need for implementing additional controllers at the system level. These bus filters are very specific to the target platform and to the vendor, and for the target platform, the Musca B1, there is an MPC and a PPC. Just to conclude this section, what we can learn about interrupt handling. So for those who know the ARM-v7-M architecture pretty well, they know there is an interrupt controller named Nest Vector Interrupt Controller. So there is a vector table tied to interrupts available on the platform. In the ARM-v8-M architecture, there is a vector table per security state, and NVIC was extended also to allow configuration of interrupts as secure and unsecure. And secure interrupts can have higher priority than non-secure interrupts, just to avoid any kind of denial of service attack. So let's talk a little bit now about the security state of TrustZone and what we have learned so far. Well, my intention with this slide is not to diminish the value of the technology, neither the value of the existing solutions, but the sad reality is that over the past years, TrustZone-assisted TEEs have been successfully attacked hundreds of times. And to understand the extent of the problem, and in the context of the PhD of another of my students, we have performed the most extensive study to date of existing security vulnerabilities affecting TrustZone-assisted TEEs. This work was accepted and presented at the IEEE S&P Auckland last May, and in this work we have analyzed more than 200 vulnerabilities spanning across different source CVEs, SVEs, paper, blog posts and whatever, and we have reverse engineered 5 commercial TEEs: Qualcomm, Trustonic, OPTE, Huawei and NVIDIA. We have also classified these vulnerabilities among 3 main categories: architectural, implementation and hardware. And I would like to highlight that one of our conclusions was that more than half of those vulnerabilities are rated as critical and severe. For the remaining of this section, I will focus on the architectural issues, specifically on those that contribute to the attack surface. Well, the first conclusion is that TEE interfaces have become pretty large. First, the number of commands handled by trusted applications tend to be fairly large. For example, the Widevine TA implements 70 different commands, like this one. Second, the TE kernel exposes a large number of system calls to TAs. For example, the Qualcomm TE kernel provides to TA 69 system calls. And third and last, the access permissions to TE system calls are frequently coarse-grained. For example, the Trustonic TE shares a fingerprint device driver with almost all TAs. So we are in a position to say that wide interface in TEE components promote designs more prone to vulnerabilities. And there is a very interesting work published by Jan van Bulk at CCS named A Tale of Two Worlds, which precisely focus on this problematic but for Intel SGX and RISC-V. So the second conclusion is that TEEs have very large TCBs. Part of the design philosophy of a TEE system is that they should rely on a small TCB. However, we have measured binary size and the number of lines of codes for the 5 commercial TEEs. And what we have concluded is that TEEs are fairly bigger than similar software systems. And depending on the system configuration and the number of TAs, they may reach several megabytes. So there is a common belief that TEEs are highly secure because they present a small TCB, but the numbers and the facts demonstrate precisely the opposite. TEEs are too big and too complex to be secure. So just to wrap up this section and to put in perspective what you can find out there specifically designed for the TrustZone-M MCU. So first, the ARM Trust Firmware M or ATF-M provides a reference implementation of the secure world software for ARM v8-M MCUs. If you take a look at the source code and if you compile the existing project, you can easily realize that first, the significant amount of code intended to be deployed on the secure side, and second, that the generated binary can easily push the TCB of your system to 100 kilobytes. Second, the KNIB-M, which is the specific answer from TrustZone to protect the TrustZone-M MCUs, is being adapted from the existing KNIB TE for mobiles. Last but not least, I want to stress that more dangerous than large TCBs and interface is the confusing message ARM is currently spreading in terms of what should be deployed on the secure world. The two images were extracted from the official documentation from ARM that you can find on the official TrustZone-M website. And if you take a look, you can easily state that ARM is suggesting people to encapsulate entire OS kernels and the communication stacks on the secure side. This is a very confusing message and just highlights the problems developers are currently facing on deciding what tags shall we put in what basket, and especially when there is more and more features to consolidate in a single device. So we by no means intend to diminish the value of these solutions, and I would like to make very clear that we haven't performed a deep study on these solutions yet, but with what we have seen so far, it is very likely that the same problems will happen again in the future. So we are now in a position to say that the dual world model provided by TrustZone is falling short to address the increasing requirements of modern IoT devices. So I will hand it over now to Daniel, which basically will explain the design, implementation and evaluation of our solution.
Hello everyone, I hope you are enjoying our talk so far. I will present the microtangle infrastructure which was born to empower TrustZone-based systems with multiple trusted environments. As Sandro has presented to you, one of the root causes of the prevailing vulnerabilities in TrustZone-based systems is related to the traditional dual-world model. If the new solutions emerging in the TrustZone-M ecosystem are following the same bumpy path that the big TrustZone has already traveled. So one might ask, is that a better solution? Yes, with microtangle it is possible to break down this dual world model barrier. We follow a zero trust approach by isolating each piece of code on its own equally secure execution environment. To enable multiple worlds on TrustZone systems, microtangle kernel solely relies on the hardware hooks provided by TrustZone. These are the top 10 high-level details of microtangle. First, microtangle sits on the secure side and it's the first software component to run. Worlds will run one at a time in a round-robin fashion in the non-secure state. The worlds waiting for their slot time are safely preserved on the secure side. To achieve this, at each scheduling point, the SIO is set with memory settings associated with the world to be resumed. In the same way, the security state of interrupts will also be changed. During this context switching, each world context will be saved into memory. The scheduler component is supported by the system timer, which is banked between states in ARM v8-M architectures. 7. The bus filters, which extend the secure state to the remaining SOC resources, are configured in boot time to match the world's memory space. Regarding the configuration of microtangle, it is done steadily through a simple flat file where we set each world memory area interrupt among other options. MicroTango was deployed in the ARM Musca V1 platform, which was the first ARMv8-M silicon platform available in the market. To better understand MicroTango design and implementation, let's bear in mind this use case over the next slides. In this example, MicroTango is configured with two worlds. The first is a bare metal application featuring a serial terminal. The second one is an application blinking an LED every 1 millisecond. The UART device is assigned to the first world, and the PWM and timer device are assigned to the second world. During boot, MicroTango will start by configuring some CPU options such as enabling all fault handlers, disabling system reset from the non-secure state, and prioritizing secure exceptions over non-secure ones. Then, the system timer will be initialized with the selected tick time for the system. On the next step, MicroTango will prepare the world's control block. This is a data structure used to save or restore the world's context. Each world's SOE memory regions, vector table, initial stack pointer, among others, will be initialized to allow fast context switching between worlds. Before jumping to the non-secure state, the SOE will also be set with the memory regions belonging to the first world to run. And finally, MicroTango will kick off by first enabling system timer and then forcing a jump to the reset handler of the first world to run. A non-secure function call will be issued, which will result on the transition between the secure to the non-secure state. In the end of the boot stage, this is the state of our use case. World 1 is running the non-secure state, and while World 2 is waiting for the next scheduling time slot. As we shown before, the security state is memory map based. The layout of Musca V1 IDAU divides each memory region in secure and non-secure areas. After the MicroTango boot stage, the configuration of the SOE will overlap these default settings, with the final memory layout. Each world code section is placed on flash, where World 1 is marked as non-secure. Data section is placed on the SRAM memory, and one bank, which is tightly coupled to the CPU, is reserved for MicroTango code and data. This ensures that almost all kernel instructions takes one clock cycle to run, with no additional overhead due to bus or memory stalls. Peripherals assigned for each world are marked with their respective security state. To sum up, during boot time, MicroTango will set up the memory space through the configuration of the SIU. The non-secure execution context for the first world to run is prepared, and the remaining worlds are suspended in the secure side until the next context switching. To ensure that isolation boundaries are expanded to the other SLC resources, bus filters are also configured to match the world's memory and device settings. We assume that other bus masters besides the CPU, such as a DMA controller, are confined to the secure side. This prevents the reconfiguration of each bus filter during the context switch, avoiding additional performance penalties. At this point, you can now imagine that most of the work performed by MicroTango during runtime is the scheduling of worlds. So, what does really happen during a scheduling point? The schedule algorithm was designed to be as simple and fast as possible. There are four main steps before a new world to be scheduled. First, the CPU context of the suspended world must be set. We do this by setting the state of the CPU and system registers as well as interrupts into the world's control block data structure. Next, a new world is scheduled in the round-robin fashion. And before resuming the new world to run, the SLU must be set with the world's memory regions. Bringing back our use case, after the scheduler performs its job, the World 2 will be running in the non-secure state and World 1 will suspend in the secure side. Now that you have a good understanding about the scheduling algorithm of MicroTango, one question can be raised. What happens if an interrupt of a suspended world takes place? During the context switch, we must disable and retarget interrupts from a world that is being suspended. At least for now, when an interrupt of a suspended world takes place, it will only be served when the world is resumed on the next scheduling point. Sure, this is not desirable, but it was workable at least for this embryonic stage of MicroTango. To clarify, let's see an example. Imagine the following situation. MicroTango is configured with two worlds, one RTOS with a timer interrupt, and another world with a communication stack and an SPI interrupt assigned. As you can see in the chart, the SPI and timer interrupt were triggered while their respective world was suspended. In that situation, the interrupts will only be entering their handler as soon as their world is put in context. Nevertheless, we are currently working on a new and improved interrupt handling mechanism that enables a preemption behavior on microtangle. This preemption behavior will be priority-driven, which allows a higher criticality world to preempt a lower criticality world. Let's recall the same example, but now world 1 has a higher priority level than world 2. In this situation, if the SPI interrupt is triggered while world 1 is executing, the interrupt will only be served when world 2 is scheduled. If the opposite happens, the second world will be preempted by the timer interrupt. The schedule will put world 1 in context to respond to the interrupt request. The second world will be resumed as soon as the timer handle finishes. After diving into microtangle architecture, I will now present the evaluation results, which you consider to be really optimistic. Our experimental setup was the following. We are using an ARM Musca-B1 platform, which implements the SSE200 subsystem that features a multi-core subsystem with two Cortex-M33 processors. We use data watch point annotation from the debug component to measure the performance overhead of microtangle. And by using a third-party tool, we assessed the TCP size. For the performance evaluation tests, we have used three different configurations for microtangle. One with 2 worlds, a second with 3, and the last one with 4 worlds set. Our goal was to show that the number of worlds to be scheduled does not impact in any way the performance overhead of the microtangle kernel. During the development of the microtangle, we tried to keep the TCP as small as possible, as well as the numbers of lines of code, since code complexity is typically a natural enemy of security systems. In that sense, microtangle relies on the principle of minimal implementation, striving to reduce the amount of code that executes at the highest privilege level, which is reflected in a TCP size of around 6 kilobytes with less than 900 lines of code. We also measure the performance overhead associated with the microtangle kernel. We consider performance overhead as the amount of time that the kernel spends while switching between worlds. These are the values that we obtain. As you can see, the system does not suffer any performance penalties for the different system configurations. In fact, the context switch time is precisely 110 clock cycles for each of the scenarios. To achieve such low overhead, the scheduling algorithm was completely written in assembly and the kernel is running from a TCM memory. To sum up, with Musca-B1 platform running at a CPU frequency of 160 MHz, the microtangle has a performance degradation almost residual. Besides, these results are completely independent of the system settings. We will now present a small video showing a demo from microtangle. The video that we are about to see features microtangle with the following multi-world IoT stack. First world features a bare metal application blinking an LED every 1 second. The second world encapsulates a Zephyr RTOS, which is controlling a servo motor and communicating its rotation behavior through a serial terminal. The third world is a simple command line, and finally, world 4 provides to the system a TCP IP connection. This is the microtangle configuration file, which details each world settings. Memory regions, vector table on device. First we have the world 1 structure. This is world 2 structure. World 3, and finally we'll have a world 4 structure. Now we will be building microtangle and loading into ARM Musca-B1 platform. Now the full system is working. This is world 1 blinking an LED every 1 second, Zephyr controlling the servo motor and communicating its rotation behavior through a serial terminal, World 2 which provides a command line, and World 4 that provides a TCP/IP connection to the system. And the full system looks like this. World 1, two, 3, and finally World 4. Wrapping up, our takeaway points are: we hope that you have been clear on why we believe that the traditional TrustZone dual world model is falling short to address the increasing complexity and requirements of modern devices. MikroTango solely relies on the hooks of the elephant in the room, TrustZone, and we have demonstrated a solution that is capable to extend the dual world model into a multi-world approach. And third, we evaluate MikroTango in a real-world platform and targeting a real use case scenario, with achieving real promising results. I'm sure that we are all convinced that security doesn't always need to come at a significant cost. In this talk, we have presented the first multi-world TEE for modern TrustZone-M devices, which are expected to be deployed on billions of tomorrow's ARM microcontrollers. Our ongoing work consists on wrapping up the first release version of MikroTango as soon as we finish the new interrupt handling mechanism. If you are interested, follow this GitHub link. We are also working on porting MikroTango to other commercial platforms. And finally, the next major steps will focus on multi-core support and a scalability analysis to improve predictability and extend the target to mixed criticality systems. Thank you all, and I hope you enjoyed this talk.